Morning, Andre.
Hi, Chloe. Good morning.
How are you?
I'm pretty good. How about you?
I'm doing okay. I can't have my camera on today, but I'm looking forward to your presentation because I don't know anything about how control flow works in R.
Actually, you know everything about control flow. It's just the name that is confusing.
I don't know. I've always tried to do like for loops and whatnot. They're not nearly as
Hmm.
intuitive in R as they are in other languages in my experience.
Yeah. Well, I tried to present what I understood and eventually learn from you and other participants.
Well, we'll give people a minute or two to show up and then you can get started.
Good.
Good morning, everyone. Give it one more minute and then we'll get started. Okay, why don't we go ahead and get started? So good morning, everyone. Apologies for being camera off, but I have someone working in my apartment right now. So thank you all for being here. And I'm excited for today's presentation on control flow by Andre. And I just want to mention, if you've not signed up already for presentation, please think about signing up and presenting one of the chapters. Uh, you can sign up there. And thank you to everyone who has signed up. And with that, yeah, take it away, Andre.
Okay. Thank you so much, Chloe. So can you see my screen right now?
Yes, we can.
Okay. So yeah. So it is a real pleasure to present this chapter on control flow. And my apologies because I have been pretty liberal in including some content that doesn't initially belong to the book itself. Because if I didn't understand a concept, I went on the internet and I found some information that I included. So you may not find some of these texts like this introduction if you are following along with the book. I just wanted to mention it before I start. So control flow, I didn't know what it is. It is a pretty new concept to me, but actually it is in computer science, how, the order in which statements and instructions are executed in a program. So it determines how the program progresses from one instruction to another based on certain conditions and logic. And control flow mechanisms allow the developers to create dynamic and flexible programs that can make decisions, repeat tasks, and respond to various inputs. So this is from Codecademy. So as you can see, uh, intuitively, we can refer, if we use R, for instance, we know for loops, while loops, repeats, if. So this is uh, all about control flow. So in R, we have two primary tools. The first one, we call them choices, like the if loop and the switch function that we will develop later. And the second type of primary tools are called loops, the while loop and the for loop, for instance. So now let's talk a little bit about the choices first. So if we take choices as we saw, we have if, the if function, for instance. What it does is, well, we have a condition. If we'll evaluate a condition, and if the condition holds true, it will do something about it. It will execute what we call a true action. This is one form of if, the if statement. And we can use these codes to evaluate, for instance, to just see what it does. So in the first line of code, first of all, the condition within the parentheses will be evaluated. And if it is true, it will proceed with displaying this one. Otherwise, it will do nothing. And as we can see, this one is executed. 5 is greater than 3. And the two other lines of code did nothing because the condition within the parentheses is false. Therefore, it will skip this statement, and the following thing that happens is nothing. However, do nothing is actually not do nothing per se, because in the background, it will do something that we will see later. So this is one form of if, the if statement. Another form is if condition, do the true action, else do false action, which basically means if the condition is true, proceed with the true action, otherwise proceed with the false action. And here we can illustrate with the same examples as we used before. If 5 is greater than 3, display 5 is greater than 3, else say display 5 is not greater than 3, which of course is false. So in this very first statement, since the condition is true, the very first action is implemented and anything else is skipped. But the two following lines of code, condition is false, therefore it will skip the first, which is with true action, and proceed with the false action. 5 is not greater than 3, and I'm just kidding. So typically the actions are compound statements contained in a curly brace. Let's say we have grades from students. We can create a function that takes as argument x, which is the grade of the student in question. And we define if the grade is greater than 90, the student has A. Else, so if the grade is above 80, but of course below or equal to 90, it will be a B, and so on and so forth. So as you can see, control flow is how the computer will execute one line of code and move on to another line of code based on certain conditions here. So as long as this condition is true, then it will display this one and skip anything else below. If it is false, it will move on to the second one and evaluate one. Oh, is it true? Yes, I display B. Otherwise, I skip and I move on with the next codes. And we can just illustrate it with examples. So we already created the function grade that takes argument as argument the grade of a student. For a student that has 98, we expect to have A. If the student has, let's say 78, it is below 80, but above 50, then it will necessarily have, I guess, yeah, yeah. What did I say here? 70 is A, B. Oh, yeah, of course, yeah. It is above 50, but below 80. So it will be a C. And if it is below 50, that will definitely be a F. But of course, it will evaluate all of the conditions before it goes to the F. it turns out that we can take the result of the statement and assign it to a variable, for instance. Here we have if true, the condition is already true, so the whole line will return 1, of course, and we can take the 1 and assign it to a variable name called x1. In the second line, condition is false, therefore skips 1, and the result will be 2, and we assign it to x2, and we can create a vector like that, 1 and 2. And the authors recommend to assign the results of if statement only when the entire expression fits on a single line, as we can see here. Otherwise, it can be pretty hard to read. I said before that if you have if a condition is false, the line of code implemented is like do nothing between quotes, but actually under the hood, it does something. It provides a null, but it is not just displayed. Let's say here 5 is less than 3 is a false condition, of course, because 5 is greater than 3. Therefore, it will not implement the true action, and it usually just shows nothing, as we can see here. But under the hood, there is a null that is displayed that we can either show with, by adding parentheses like that, or by using the print function here. It is the same. So things, functions like concatenate or paste drop the null inputs. This allows for a compact expression of certain idioms. Let's say we have a function here, and it takes as arguments the name and the birthday with a default value being false. And we want to print a statement hi, concatenate strings here. The first one being hi, followed by the name of the person, sorry, followed by a statement that says if it is a birthday, the birthday of a person, then add this line of these strings. So if we take an example with this one, with a greet function, and we say we provide only me, which is obviously the name of a person. The default of birthday being false, what we have here is it will concatenate hi plus the name of the person here, which is me, and the default being of birthday being false, with the if will evaluate false and then display a null, which is invisible actually, and this function will just drop it, and we'll have something along the line of hi me. In the second line, hi Maria, and birthday being false, the same thing. However, the third line will be hi Faime, and since the condition is true, it will display and happy birthday, as we can see here. Hi me, hi Maria. However, we should be careful because if the if function has some, it should evaluate a thing, the condition, the thing that is between the parentheses should be evaluated into a single true or false. And single is very important because if you have like a vector of true and false, it will not work with if there is another function that is built for this kind of things. So if we have a character and we put inside the parentheses, if it doesn't know what this one means, is it a true, is it a false, it cannot define, therefore it will give an error because argument is not interpretable as logical. Another invalid input is empty vectors like this one. An argument of 0 length. if we put more than one single true or false, it becomes some type of vector. And if it is not built for that, it will display an error as well. Same as NA is eventually if, and we have an NA, the condition is NA, so we don't have any condition to evaluate, and it will return, of course, that there is a missing value for true or false. That is required to be evaluated before anything can be done. Interestingly, what I found interesting is that actually when you take numbers, any number that is not a zero will be considered true, and zero is the default and is a false. So if you take, for instance, if zero, this one would be the condition is false, therefore it will skip this one and display nothing, or you can reveal the null, the invisible null that is printed here. However, any number that is not a zero, whether it is a decimal, an integer, or any negative number will be considered as true, and then the statement will behave as such, as you can see here. So I mentioned previously that for if to work, we need to have a single true or false, because if we have a vector like false, 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 true, false, if is not built to handle this. There is another form, there is another function that is called the vectorized if, and it is if else. And we can display here with a couple examples. Let's say we have a vector of numbers, a sequence of numbers from 1 to 10. And here, let's comment out this line. And we want to test this condition. So x modulo 5 equal to 0. So this will eventually return a logical result. It is either true or false. The modulo function is just the reminder when you divide something by something. Let's say if you divide 6 by 5, so 6 modulo 5, you have 1 and a reminder of 1. So 6 modulo 5 equals 1. For numbers that are below 5, it is the same thing. If you take 1 in the sequence of numbers, if you take 1 and you know 1 modulo 5, you have 0 and a reminder of 1, right? And you take this modulo and you verify this condition. 1 is obviously not equal to 0. Therefore, it will return a false. We can just test it like that. So 1 will be false, 2 false, 3 false, 4 false. But 5 will give you true, because 5 modulo 5 will give you 1 with a reminder of 0. 0 equals 0. That holds true, true. 10 is also true. So if we wanted to, let's say, use if, it will just throw an error, because the statement says, okay, this one condition, if it holds true, then show this one. Otherwise, return the character of the number. If we use if, it will just say unexpected. It throws an error because it's not built for that. We need something else, which is the if else function to execute. So first one, condition is false, skips this one and returns 1 as a character, and so on and so forth. And for 5, we have a true condition, therefore we return XXX as a character. Another example here is the X, it is the same thing, just X is comment. This one will return either when the modulo would be 0 or not. If we take 1 modulo 2, it will return 1, which is not equal to 0, and it return then a false. So if you take even numbers, all of them will give you a 0 and a true condition. Odd numbers will give you something that is different than 0 and a false condition. And we will have like false, true, false, true, false, true. Here, a vector of false, true, false, true, false, true that we can use if we want in with a if-else function. It will return even or odd. So another, how does if-else how does if-else deal with missing values? Interestingly, as we have seen, if will give you an error, but if-else will return actually an NA. You know, it just preserves, it propagates into the output. So this is for vectors of logical values, false, true, false, true. One way to handle them is if-else, the if-else function. But there is another case that is very interesting. It is the case when function from the dplyr package within the tidyverse. It is a very versatile and very important, a very useful function that is applicable in so many ways. Let's say we have a database of students with grades we generated randomly, and for the sake of reproducibility, we set seed, and then we have the students with their scores and their IDs. So we want, as we've seen with the function here, let's show. Yeah, here we built a function that can give you I don't know how you call this one. Is it the grade? Yeah, depending on the score of the student, A, B, or C. We can use the case when function to do it pretty easily, actually. So we mutate being that we create a new column called grades. And here is the control flow. If the grade is above or equal to 90, then it will be, if the score is above or equal to 90, therefore the grade will be A. Otherwise, evaluate this function and give a B, or and so on and so forth until you exhaust all the options. And to be sure that you didn't leave anything behind, we always end with true. In the case something odd, like there is a score missing or something like that, we have something to fall back and not to give any erroneous results. And as you can clearly see here, a score of 80 will be B, 64 would be D, and so on and so forth. This is another pretty useful function, and this is what they gave us example in the textbook. So from a sequence of numbers from 1 to 10, if the number modulo 35 is equal to 0, if this condition holds true, write this burst, otherwise proceed with the next line, otherwise proceed with the following line, and so on and so forth. So if you take 1, for instance, 1 modulo 35 would be 1, which is obviously not a true condition. Therefore, it will skip this one and evaluate here. Not true. Okay, not true. Is it an any? Absolutely not true. Therefore, we return 1 as a character until we reach 5, and we have a true condition, and we display phase, and 7 as well. And 10, of course, 10 modulo 5 will give you 2 with a reminder of 0, and this condition will hold true. And you also have fees for 10 here. So this is a case when, for instance, that is another function that allows control flow. Using vectors, actually, here we don't have a single true or false. And another useful function is the switch statement. Switch statement let's say it's a compact special purpose equivalent that lets you replace code. Like, let's say we can create a function that takes x as an argument, and we say if x equal to a, then option 1, otherwise option if it is b, option 2, etc., etc. It's a pretty long code. We wrote a lot, and it achieves the purpose, but it's not let's say efficient, I would say. I don't know if it is the right word. Yeah, if you have A, it will display option 1. If you have B, it will display option 2, and so on and so forth. But we can replace all of these codes with a simple line of code like that using the switch function. A equal option 1, B option 2, and so on and so forth. And as we can say, option 1 for A, option 2 for B, etc., etc. And a warning, they say the last component of switch should always throw an error, otherwise unmatched inputs will invisibly return null. Here we don't have C. Therefore, if we want to implement the switch function, it will return null because we didn't define what C would be. A pretty useful feature of the switch function is if we have multiple inputs that have the same output, we can leave the right-hand side empty of the equal sign empty, and the input will fall through to the next value. And this mimics the behavior of C's switch statement. So let's say here we have a function x being the number of legs of the animals, and we say switch and the argument x. We all know that cows, horses, and dogs have 4 legs, so we don't need to type cow 4, horse 4, and dog 4. We just leave these empty. It's all, all of these previous, we take the last value, say for human and chicken. So if we wanna return the number of legs of a human, even if we didn't precise here, it will show us 2 legs. And this is kind of it is true that it is useful, but of course, if you make a mistake in one of them, it will propagate to the other ones as well. Let's say we made a mistake and we typed 3 legs for chicken, and we want to return the number of legs for human beings. We will unfortunately have to deal with 3 legs. So it's good, but it has, I think it has its backsides as downsides as well. So it is possible to use switch with numeric values, but it's harder to read and has undesirable failure modes if x is not a whole number. So an exercise, what type of vectors does each one of these call? So if we recall, if else we first evaluate the function, is it true? If it is true, it will return the true action, otherwise it will return the false action. So here, the statement will obviously return 1, which is a numeric, which is numeric actually. The second one will return no, because it is false. The condition is false. And the third one is an NA. And if it is an NA, it will return an NA. So we can just check all of them here. The first one we give a numeric. Second one will give a string or a character, yeah. And the last one will definitely either an any, which illogical, let's say. Oh, okay. Illogical any, okay. And this is some kind of these codes, this line of codes. If you have a logical an empty logical vector as a condition, it returns logical 0. If your condition is if it is not a number, if else we'll consider this one as an NA and return any. Not a character is also any. A string will return a any. But interestingly, true will return true, and then proceed with the true action, as we can see here. So the second exercise is we have a vector of numbers from 1 to 10. And here we have if, not if else, but if length of x, not empty, otherwise else empty. So we've seen before that any number that is not 0 will return true. And length of x will just give the length of the vector, which in this case 10, right? Because we have a sequence of numbers from 1 to 10. So 10, therefore true, and we have not empty. A numeric vector gives this is an empty numeric vector, which is evaluated as 0. Length of x here is 0, therefore condition is false, and we will not implement the true action. We skip to the next one. So I think I'm I'm done with the choices so far. I just want to return back to precise that the control flow have two primary tools, choices and loops. I'm already done with the choices. Any questions so far, or if the way I'm presenting is clear, or if I need to improve before I move forward with the loops?
Very clearly presented, Andre.
Yeah, I think you're doing a great job so far. I'm following along just fine. This is great.
Okay, well, thank you so much. So I will move forward with the loops. So after the choices, we have the loops, and we have for loops. The for loop first. How does it work? It is just for each item in a vector, do something. This is what it means. So let's say we have a vector, sequence of numbers from 1 to 3. In this for loop, the for loop, what it says is for each one of these items in 1 to 3, just print them, and we eventually have 1 to 3. I is arbitrary because we could have chosen K or J or any other number. It would work the same. Doesn't matter. As long as you put the same thing, you cannot put I in on one side and put anything else. It is so an error. And what is very important to mention is that when we are iterating over a vector of indices, we can use these we can use very shortened variable names, but we have to be careful because anytime that it is iterating, it's overwriting any existing variable with the same name. And we can illustrate here with this one. So we have a variable that's called I, and we assigned 100 to it. So if we didn't have this for loop and we call I, we would definitely have 100, right? Because I is takes the value of 100. But now that we are implementing this for loop, in this for loop says for each item called I within 1 to 3 range, do nothing because it doesn't precise any action to be done between the curly braces. However, what the for loop does is each time that it makes the iteration, it updates the value of I. So the first iteration, I, instead of being 100, will now be 1. The second iteration will be 2, and the third iteration will be 3. And when we call I, instead of having 100, it will return the third iteration, the result of the third iteration. That is not displayed, but actually I has been updated. If we had like 4 or 5, it will be the last iteration and it will return 5. So and it is very important because if you look at the environment, we could have maybe created something that we called I that is of importance to us, and we make a mistake to use the same letter, and it will just overwrite anything that was there. So the curly braces contain the body of the loop. Since the body is empty, so no operation was performed, but I is updated anytime. So there are 2 ways to terminate the for loop. We have next and we have break. And we can illustrate that with this function. So here we say for I in range 1 to 10, if I is below 3, next. So we say as long as I is inferior to 3, do not do anything that is below. Return back to the sequence and evaluate. Is the following I, because I has been updated, is it still below 3? If it is, then do nothing until we have a condition that is here false. Therefore, we will start doing something. This is what the next means. And the break, if this condition is true, we break. And we can illustrate that with, first iteration would be, so if we take, for instance, 1, this condition is true, therefore it will not proceed with printing 1. 2 will not do anything because condition still true. But when we reach 3, 3 is not less than 3. Therefore, we skip and we print. But 3 is not above 5. So this condition is not true. It's returned back and so on and so forth. And we have this range of numbers that are printed here. Here are some common pitfalls that they showed. I'm not really sure if I understood what they wanted to show, or if or maybe I don't understand the usefulness of it, given that maybe I've never been in a situation that I had to worry about it. So they say there are 3 common pitfalls to watch out for when using for. First, if you are generating data, make sure to pre-allocate the output container. Otherwise, the loop will be very slow. I don't know if it has to do with memory usage or something. Here we have a vector of integers, and they assign it to main, and you have a second vector, which is a list, an empty list of length means, which is 3, obviously. And for I in 1 to length of mains, which is 3, the out, so the list, I don't know how to say, like the ith value in the list would be a randomly generated 10 randomly generated numbers with mean I, and then we return out here, as we see. So this is the first iteration because we have 1 to 3 iterations, and each iteration we return 10 numbers, normally distributed with a mean that is 1. So first one, second one, and third one. And I think here they said that it was useful that we have created this container out. So, and the second warning that they say, so beware of iterating over 1 to length of x, which will fail in unhelpful ways if x has a length of 0. Oh yeah, obviously, because here if we have an empty vector, length of this vector would be 0. And if you want to iterate from 1 to 0, it should, I don't know, it will throw an error, as they say, because sequence from 1 to 0. But later they show in like later in the chapter an exercise that managed to execute all of the functions despite having to deal with this pretty awkward situation where you have to go from a sequence from 1 to 0. I will show later. And this occurs because the two dots work with both increasing and decreasing sequences. And they say that we can use this function to correct this, I guess. Yeah. But I'm not very sure if this is what they mean. So another warning that they say is to be careful with S3 vectors. I think it is Jacqueline who presented vectors. So S3 vectors include factors, date and time, data frames, and tables, for instance. And if we use them, we have to be careful because they can just throw distorted results that have nothing to do with what we wanted, and work around this by calling using these brackets, I guess, that will give the true result that we want.
So that's interesting. It's the difference in using the elements like x in XS versus versus like an integer loop like I in the second example,
Okay.
and the using the double brackets.
Okay.
No, it's interesting. I didn't know that. I usually do use the second kind of loop, but I didn't know that the first one would strip all attributes. Interesting.
Yeah, but thank you. I don't think I ever had to deal with date time data so far.
Yeah, but I mean,
So,
the date is just an example. Like attributes can be all sorts of things, like the names of a list element or a data frame or the names of a vector. Yeah, attributes can contain other things as well. So you could probably do this example also just with a named vector, looping over the elements of a named vector. A
okay.
vector that's 1 to 10, but where each element has a name. If you do the first kind of loop, I guess you would lose the names.
Oh, I see. Okay. So so the other loops that we didn't actually develop further, the while loop and also there is this function repeat. So I think you can use even for loops and while loops can be interchangeable in some cases, as we say. I don't think, I think maybe it's sometimes a matter of preference, or sometimes there are some exceptional cases where you cannot use one instead of the other. So a while loop, what it does is just checking a condition, and as long as the condition is true, do something. Like here we have a counter. We assigned one to the variable counter, and we said as long as the counter is below or equal to 5, print paste the current counter value given the value of the counter and increment by 1. And of course, if this condition is false, it will stop by itself. And we have, yeah, 1, 2, 3, and we stop. You can reproduce the exact thing with a repeat, for instance. Here we say repeat print paste current counter value counter increment, but we need to precise that if the counter value is above 5 to break exit the loop. Same outcome using 2 different functions. And yeah, so well, I'm almost at the end of the presentation. So there is this exercise, and they ask, why does this code succeed without errors? Because we saw, as I was mentioning previously, if we have a weird sequence from 1 to length of x, x being an empty vector, we know length of x would be 0. So how does it happen that we can still have some kind of output if we go from a sequence from 1 to 0? Here it shows any, it doesn't show an error. So what they say here, the explanation is, so the code snippet succeeds without error or warning due to the behavior of R in handling empty vectors and the operations performed on them. So here we have an empty vector, and length of x will definitely be 0 because it has no element. In the second line of code, we say a vector list, and the list also has a length of x being 0. So the length of this vector will also be 0, matching the length of x. And here we say so length of x for the for loop for I in 1 to length of x. So this is where the behavior might seem to be tricky at first glance. However, the key here is understanding how 1 to the length of x evaluates when x is an empty vector. Since length of x is 0, 1 to length of x generates a sequence from 1 to 0, which is integer 0 vector in R. And we could have used the sequence underscore along x to correct this. So this effectively means that the sequence is empty and the loop has no iteration to execute. As a result, the body of the loop is never executed. And the last function here, the last line of code is intended to square each element in X and assign it to the corresponding position in out. However, since the loop body never executes, the loop has no iteration, and this line of code is not run at all. So the final line simply returns the out list, which remains an empty list as it was initialized. So therefore, the code succeeds because it essentially attempts to perform operations on an empty set of elements, and the loop that would perform these operations never entered due to its controlling sequence being empty. And R will handle such cases gracefully without throwing errors or warnings, as the operations defined within the loop are syntactically correct, but they just are not being executed. So this is a pretty lengthy explanation, but yeah, so it's kind of a case where something that should have not been executed is still executed based on the rules that are applied. So the last, I think the the second exercise is when the following code is evaluated, what can you say about the vector being iterated? So my understanding here is that, as I said, that in this loop, x takes on the values of initial x 1 to 3, indicating that it is evaluated just once in the beginning and not after each iteration. So x in for x in XS, what they do is they take XS and they assign the values of XS itself and x times 2, which will give, if we take the first iteration, we will have 1 here, XS is 1, and we have x times 2 and gives you 2 with the first XS here, and then times 2 gives you 4, and 3 gives you 6. It does it once, but XS is never never updated. This is my understanding. That's why it just doesn't go in something that is infinite, you know, doing this one and then going back to check the new XS values and then etc. etc. But I don't know if it is what it really meant here. And here, what does the following code tell you about when the index is updated? So here, in a for loop, the index is updated in the beginning of each iteration. Therefore, reassigning the index symbol during one iteration doesn't affect the following iteration. So again, we would otherwise run into some kind of infinite loop. So the first time I would be I times 2, and then we print 2, and then go to the second value, which is 2 times 2 gives 4. And the last iteration, we consider the last value, 3 times 2, and we print I, and we have 6. So the last quiz is what is the difference between if and if else? As we've seen before, if cannot handle a vector of logical values. For if to be able to run, we just need one true or one false. But with if else, we can use vectors. And what does x switch x x equal with precise nothing, y2 z3? So why does it return to? We've seen with the switch function that if you have let's say a set of variables that are following each other and taking the same value, you don't need to input the same values for all of them, because the last one of them, the value of the last one of them, we just propagate backwards. So even if we don't precise 2 here, as long as the last one, which is y, takes the value of 2, it will just x will also be considered as 2. So just a summary of all of this. So what is control flow? Control flow just refers to the order in which statements and instructions are executed in a program. And we have choices. And if we have just a single true or false, we can just use if. If condition is true, true action. This is one form of if. The second one is if condition, true action, else false action. If we have a vector, we can use if else and test the condition first. If it is true, we return yes. Otherwise, we return no. And we return back to the vector and take the following value, test the condition, proceed, and so on and so forth. We also talked about the case when function, which is very useful, evaluate a condition. If it is true, return the output, otherwise move to something else, and so on and so forth. And finally, we have a switch function, and we have x that can take any and depending on the value of x, we can display the output that is corresponding to it without having to write lengthy functions as we've seen before. And for loops, so we have choices and we have loops. Loops, we have the for loops, which actually is implemented this way. For any item in vector, do something. For the while loop, as long as the condition is true, do something. And the repeat function repeats something under some condition until I say break. And then you stop at that time. So this is the end of my presentation. I hope it hasn't been too confusing to myself and to others. And if there's any question or clarification, they are welcome.
Nicely done, Andre.
Yeah, this was a truly excellent presentation. I just wanted to ask if there was like one takeaway you had from this, like what was the one thing you learned that you feel like is going to be really useful for you when you work in R?
Oh yeah, so thank you so much. So this is reinforcing my conviction that there's one single way of doing things in R actually. And that can be kind of confusing with people with a beginner or intermediate level of understanding of this programming language, right? Because you can read a document or a website and they show you something and you go somewhere else and they use another function or another way of doing things, and it can be overwhelming, right? At some point you don't know which one. So the takeaway would be, and an example here is uh, the while loop and the repeat function, right? They're doing the exact same thing, right? So it would be just to take whatever is easy for me and implement, because yeah, you can do the same thing in so many ways. So this is my takeaway.
Thank you.
One of the takeaways for me was just how much sort of our dogma has changed since when I started. Back when I first learned R in let me think, in about 2006. People were being taught to avoid using loops like this, that was not the R way, and that you should instead try to use implicit loops, which which we do still use, which are like, well, there's no example of it like this, but things where you don't actually write out a loop, and then these special loops based on the apply family. There's apply, sapply, vapply, lapply, all of these things. And I think since then, R has gotten much faster at executing loops like this, and they're also much easier to understand and to read than fancy vapply statements. In a lot of cases, they can still be convenient sometimes for doing something in one line of code, but they're definitely a very particular way of thinking that takes getting used to in a way that loops, which are the same in all kinds of programming languages, don't. So yeah, I like loops. They're very declarative and clear what they do.
Okay.
Cool. Any other final thoughts? We've got like 1 minute left, so. Okay, if there's nothing, thank you all so much for being here. We'll be meeting again next week on Friday. Marcel will be presenting. believe he'll be presenting on functions. So I feel like that's one you don't want to miss. I feel like if you're here for anything, you should be here for functions. So
Who's presenting that?
Marcel,
Oh, cool.
yeah. So thank you all so much for being here, and thank you again to Andre for presenting. And I hope you have a nice weekend.
Thank you.